Good afternoon. Good afternoon. Hope all is well. Hope everyone is doing all right.
Good afternoon. Doing well. And yourself?
I am good. I am good. Just rushing through traffic trying to get here, man. I'm glad I made it. All right, let's see. Hey, hey, hey. All right. So are we ready to get rolling? Anybody have any questions or anything before we get started? Everybody's all right in my math lab? Good.
There's an assignment up there. I think it says like assignment 1 or
Mhm.
something. And it's got like, I guess it's questions from like 3-1.
Mhm.
I missed the last class. Did you give a due date for that?
No, I didn't assign that to you guys. It's something I had from my last semester. Normally, if I had 16 weeks, then I would give you like extra assignments and stuff, but we only have 8 weeks, so we just sticking to my math lab. Just
Okay, thank
regular
you.
assignments. Yep, not a
Okay,
problem.
thank you.
Thank you for asking. All right. So Monday, we are off. So don't forget that. If I remember, I'll probably shoot you guys an email just to remind you that we don't have class on Monday. Let's see. So we knocked out all of chapter 3 last class. Correct me if I'm wrong. Of course, I believe we did of the 3-5 last class. All right. So, and this is just a summary of what's done. Now, once again, you guys don't have to do that assignment 1. We're just doing your math lab homework, definitions, and then you have that test 1. All right. So we'll go ahead and look at 4 today. On Wednesday, priority is to address any questions, so I'll be looking to see if you guys have any questions on anything. So that, that will be the first thing that we'll do. I'll just, see if you have questions before we look to go anywhere further. Because at that point, we would have done lecture on 4 chapters, or 4 chapters will be what you guys are responsible for up to that point. So I do want to make sure we're straight. I'm not even sure if we're going to do anything new on next Wednesday. I just want to make sure that we all in a decent place moving forward. But we can go ahead and do 4-1. Let's see. We'll see how far we go today. All right. So 4-1, scatter diagrams and correlation. So a scatter diagram is a graph that shows the relationship between 2 quantitative variables measured on the same individual. You'll see what that means in a second, of course. All right. So each individual in the data set is represented by a single point, not a point. So we're going to have 2 variables. It's going to be our explanatory variable and our response variable. Talk about the difference of the 2 in a second. Of course, let me know if I go too far up, if you're copying something in the black. So your explanatory variable explains the value of the response variable, and your response variable is explained by the explanatory variable. So in other words, we'll have an example of a golfer who hits the ball, and you record how far or the distance the ball travels. So the explanatory variable is how fast or how hard he swings the club, and then the response variable is how far the ball travels. So how far the ball travels is explained by, how hard he hits the ball. So that would be the difference between explanatory variable and response variable. the response variable responds to what initially happened, and that initial thing is that explanatory variable. So your explanatory will be your X, when your response will be your Y. Then you have your domain versus range, input versus output, independent variable versus your dependent variable, and then your horizontal axis versus your vertical axis. And then the main thing that we will be using this for is your explanatory variable is the predictor, and your response variable is the predicted. That's what we will be predicting, and we'll use the explanatory variable to predict. But once again, when we put numbers on this stuff, you know, it'll sit better. All right, so right here is just a generic example of how your scatter plot will look. Those are your explanatory variable will be on your horizontal axis, response variable will be on your vertical. Then you have dots that represents your occurrence or your observations. All right. So linear relations. So when a line best sums up the shape of the scatter plot, we will consider it linear. So we have some generic examples of patterns being established by these scatter plots. So you see the first two are considered linear. The second and the third one, my eraser works, are not linear, but they still have a relationship. So you can see the arc in that third one, and then the kind of wave in the fourth one. And then you can see in that last one, there's no relation at all. So in the purple, see, I said no, non-linear does not mean no relation, it just means no linear relations. So, and we're focusing on linear relations. All right. Next thing we're looking at are associations. So if you're talking about being positively associated, that's when one value increases, the other one also increases. So if you notice down here, notice my points are going up. If you're reading from left to right, my dots are going up. So that's considered a positive association. Negative association is when one value increases, the other one decreases. So as you're going from left to right, your points go down. And that's what's happening right here. All right. The linear correlation coefficient. It's a measure of strength and direction of the linear relation between two quantitative variables. So just like before, we talked about how the population can have a different symbol versus your sample. So we have two different symbols here for our correlation coefficient. You see Greek letter rho, kind of look like the P, more like the Philadelphia Phillies. If you watch baseball, that P, that kind of cursive type P, that's actually Greek letter rho, and it represents the population correlation coefficient. And then we have R, which is the sample correlation coefficient. Now we're going to use R. That's the one we'll use, but I know the book pointed out rho, so I was just showing it to you just in case you see it in math lab. You know, it's like one of those terms they ask. But R, the sample correlation coefficient, would be the one that we use. All right, so just like we did with the standard deviation and the variance, you want to use a website calculator or something along those lines, an app that will calculate the correlation coefficient and the regression line for you. Easycalculation.com does the same thing. It calculated for you, I should say. Not does the same thing, but calculates it for you as well. Just like standard deviation and variance, all you have to do is correlation coefficient, easycalculation.com or easy calculation, and it'll pop up just like we did standard deviation. Now 4.2, we're going to talk about a regression line, but that same type of deal. You want to have calculator website or an app that is reliable that can calculate this thing for you. And of course, we'll do that before we leave, just as an example.
Professor Tucker,
Mm-hmm.
the one where it says R sample correlation coefficient, what does it say in the red? One we will use?
Well, yeah, that's the one we will use. Yep. And probably could have wrote that better, but yeah, I was just stating that that's the one we will use. Yep, the R.
Okay.
All right. Thank you. Thank you. All right. There are a few properties that the correlation coefficient will have. So talk about those. All right, so first one is between -1 and +1 inclusive. So that means it can be equal to 1 or -1. So that's why it says inclusive. So if R is equal to +1, then a perfect positive linear relation exists. If R is equal to -1, then a perfect negative linear relation exists. All right. The closer R is to +1, the stronger the evidence of a positive association. And the closer R is to -1, the stronger the evidence of a negative association. So number 6, if R is close to 0, then little or no evidence exists of a linear relation. And R just reiterates what we saw with the shapes. It says if R is close to 0, does not imply no relation, just no linear relation. So 7, it is unitless. It is a unitless measure of association, and it is not resistant. That means it is affected by outliers. One of my pictures. All right, now scroll up. All right, so next 6 diagrams, just generic representations of what it could mean for R to be a certain number. So when we look at the first one, R equal to 1, remember that's your perfect linear, positive linear association. So that's why it's a straight line. And then as you deviate and move away from 1, you start to get more spread in your points. And the more you move away from 1, the closer you get to 0. Remember, 0 means no association at all. So that's why 0.9 has a little more spread, and then 0.4 has even more spread. Even though it's still a positive association, you see that the points are still flowing up is getting closer and closer to zero. And then the same thing with -1. That's the perfect linear negative association. Then as you move away from that, you start to get more spread in your data, in your observations. And then the last two are going to be close to zero. One is an arc, so or arch, yeah, arch. And then, but there is a relation there, it's just not a linear one. And then the other one is not having a relationship at all. Table 2. There's a table we have to use. I'm trying to send it to myself real quick. All right. Scroll up, everybody good? So here we're testing for a linear relation. I think it's the last thing in this section, if I'm not mistaken. It says determine the absolute value of the correlation coefficient. Find the critical value from Appendix A for the given sample size. And that's table 2, is Appendix A, table 2 in Appendix A. So I left that out. That's why I put it in red. If the absolute value of the correlation coefficient is greater than the critical value of a linear relation, of the critical value, a linear relation exists between the two variables. Otherwise, no linear relation exists. So I had to email that, take a picture and email that table to myself. I thought I had it on this computer. So that's what I was doing while you guys were copying. All right. So directions for this example, we're going to use this on. It says determine whether the linear relation exists between the club head speed and the distance. I'm still copying those directions. I mean, not directions, steps. We're done with step 3. All right, there we go. So, and this is the example I was talking about earlier, the club head speed. That's going to be an explanatory variable. That's our X value. In other words, how fast he's speeding. For the first observation, he's swinging the club at 100 miles per hour. And when he hits the ball, the distance it travels 257 yards. And so at 102, the ball travels a little further, 264. At 103, ball travels even further, 274, and so on. So that's how fast he swings the club. The first column is how fast he swings the club. The second is how far the ball travels. So first one is your explanatory. Second one is your response variable. So we have 100, 257, 102, 264, 103, 274, 101, 266, 105, 277, 100, 263, 99, 258, and then 105, 275. All right. Everybody done copying this? Can we go to the internet? Straight. All right. So all right. So we want to find a correlation coefficient first. So I would just do correlation coefficient, easy calculator or easy calculation. And you see the first one pops up, easycalculation.com. And so here you have your X value, Y value. That's your explanatory versus your response. And you can add columns or take them away, add rows or take them away. So I believe we need 8. So all I'm doing is typing in the values. Now, if you're doing more than typing in values and hitting enter, you're doing too much. In other words, if you have something you got to program or store values this place and recall and do all different types of stuff, then I mean, if you want to do that, it's fine, but you don't have to. There are things that are easier, just like this, when all you're doing is typing in your data values and hitting enter. Always make sure you hold true to the data values. If you mess up on one digit, it will change your answer completely. All right, so I have 100, 102, 103, 101, 105, 100, 105, 257, 264, 274, 266, 67, 63, 58. So I just hit calculate and see we have our correlation coefficient here. Also recognizes there are 8 numbers. It's considered 8 observations. It's not 16. So each one in the first, those are one observation. You know, remember he hit the ball with 100 miles per hour and the distance was 257. Hold on 1 second. All right. So questions on that? Everybody good before we go to the notes? All right. All right, so see here, find the correlation coefficient. That's exactly what we just did, 0.939. That's step 1. And how many decimal places is based upon, you know, my math lab, what they ask for you. Sometimes they ask for 3, sometimes they ask for 4. Just make sure you hold true to the directions. Second step, take the absolute value of R. And so it is possible for your correlation coefficient to be negative. So they want you to use the positive representation of your correlation coefficient. So that's all they mean by that. They want you to use the positive representation of your correlation coefficient. All right. And it says find a critical value from table 2 in appendix A2. So let me show you that chart. All right. So this is from the books. It's in your appendix. It's table 2. And so just trying to magnify it. We have 8 values. And we just said that we have 8 values. So our critical value is going to be 0.707. All right. Any problems with how you read this chart? If I had 18 observations, then it would be 0.468. All right. Everybody good? Everybody okay with reading the chart? All right. Like I said, that's in the back of the book. If I remember, I can shoot that picture to you in an email, but if by some chance I do forget, always feel free to email me to remind me. But I can shoot that picture to you. But that's in the back of your book, Appendix 2, Table 2 and Appendix 2. So here in the purple, that's what I have. We have 8 observations. So got that from the chart, 0.707. Step 4, compare the absolute value and the correlation coefficient. I mean, not absolute value of the correlation coefficient and the critical value. So we established both of these already. The absolute value of R is 0.939. Critical value is 0.707. So R is greater than our critical value. Absolute value of R is greater than our critical value. Any problems so far? All right, everybody good? Everybody straight? All right, so our conclusion, since the absolute value of R is greater than the critical value, then a linear relation exists between the club head speed and the distance. All right, questions. All right, so we're good. Everybody straight as far as 4-1 is concerned. All right. Okay, so I was looking at Math Lab, looked at a couple of minutes ago, and have a lot of people that are, a little bit behind. So I'm going to give you this opportunity without going any further, because there are only 2 more sections in chapter 4. So that means we'll be done with chapter 4. So I'm trying to give you guys an opportunity to get to a good place without having so much being placed on top of you. So next week, though, we'll do 4.2 and 4.3, and then that will be it for chapter 4. So make sure you take advantage of the fact that I only did 1 section today, and take advantage of the fact that I won't see you on Monday. So you got a whole week from today all the way to the next class before, to get caught up, to get into a decent place. Even if you don't get done with chapter 3 and get all the way to 4, at least get yourself, chapter 1, chapter 2 stuff done, and then into chapter 3. Because like I said, at the end of next class, and we could have done it today, we'll be done with chapter 4, be looking to move into chapter 5. So next class, most definitely entertaining questions if you have them. And then also doing 4.2 and 4.3, which will close out chapter 4 for us. Questions, concerns, comments before we close out? Everybody good, everybody straight, everybody all right? Okay. So, like I said, take advantage of the opportunity and the space to go ahead and get caught up. Other than that, you guys have a great weekend, have a great week, have a great Labor Day weekend, and I will see you on Wednesday.
You too.
Thanks.
Have a
Take care.
Have a good day.
Thanks. You do the same.
Take care.
You do the same. Thanks.